After the Unit 11 test, hopefully, I was able to introduce the Taylor series to you. So let's review what the Taylor series is. So a Taylor series approximates a function, any function, and it approximates it with a polynomial series, a power series of x. And the very first term is always the function value at whatever our center is, plus our second term will be the derivative, the first derivative at our center, divided by 1 factorial, that's the coefficient, and then times x minus c to the first. Sometimes I just write it all as one big numerator there, but this is the coefficient, the whole thing here is the coefficient, plus f double prime of c divided by 2 factorial times x minus c squared. So always the derivative, the power, and the factorial all match. Second derivative, second power, 2 factorial, they all match every time. The third derivative divided by 3 factorial times x minus c cubed plus ... And that is the approximation for any function using a power series in x, a polynomial series. Okay? So we have to know that, super important. In many cases, the function is actually equal to the infinite series. We saw how close sine is. As it turns out, sine of x is exactly equal to that infinite series. So if you went on and on forever, those curves would line up exactly. Okay? And we'll talk more about where it's the same and where it's not later. Okay? All right. If your center is 0, we call it a different name. We call it a Maclaurin polynomial or a Maclaurin series. So whenever you see Maclaurin, just know that the center is 0. So you're centered about x is equal to 0. Okay? Couple other things here. So a Taylor polynomial or a Maclaurin polynomial has a fixed number of terms. It is just a polynomial, not an infinite series. Okay, we can denote a Taylor polynomial or a Maclaurin polynomial using a little subscript with whatever the degree is. N is the degree of the polynomial. That's often used. N is not the number of terms. It is the degree. Okay. A Taylor series or a Maclaurin series is a series, so it has an infinite number of terms. It does not stop. And lots of times you might see it denoted by P or T without a subscript. Okay? And this was, and I talked about this yesterday, this is the form of a power series centered at C. So Taylor series is a kind of power series. A Maclaurin series is a kind of Taylor series, so it's also a power series. Alrighty. Let's look at some examples. I have some info there because you know I like to talk about, I like to share with you some of the history behind some of these people who are well known for doing wonderful things. All right. Number 1, we are going to find a Taylor approximation, that's one way that they could say it, for e to the x with center at 0. So I know the form. The very first term is just f at our center. So this tells me that our center is 0. C is 0. So the very first thing I'm going to do, I'm going to write down what f of x is. F of x is e to the x. And then right next door, I'm going to find f at 0. So f at 0 is e to the 0, which is just 1. Then I'm going to find f prime of x, because we have all of the derivatives in our series. So f prime of x, the derivative of e to the x, is still e to the x. which means f prime at our center, we always want to put in our center into each of these, it's going to still be e to the 0, which is still 1. F double prime is still e to the x, so f double prime at our center is still 1. Will this ever change? No, it will not. So this just keeps on going and going forever. So our approximation for e to the x, will be, okay, here we go. We start with our constant term, and it is just our constant term, no x's. It's just our constant term. If you would like to think of it as being divided by 0 factorial, great. But I don't have to write that. Plus, now comes our first derivative times x minus our center to the first power divided by 1 factorial. Plus, our second derivative times x minus 0 squared over 2 factorial, plus our third derivative times x minus 0 cubed over 3 factorial, plus ... So if I simplify this, we'd have 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. If I went on, I'd have x to the 4th over 4 factorial plus ... and that is the power series. That's the Taylor series for e to the x. Okay? I need you to memorize this for e to the x specifically. Okay? Number 2. Let's do the same thing. Let's find a Taylor series for sine x with center at 0 still. So c is 0. I'm going to do it the same way. F of x is sine x. I'm going to go immediately right next door, and we're going to find f at our center. And f at our center is sine of 0, which is 0. Next up, f prime of x. Well, the derivative of sine is cosine. F prime then at the center 0 is cosine of 0, which is 1. Second derivative. The derivative of cosine is negative sine. So f double prime at 0 will be negative sine of 0, which is still just 0. Third derivative. The derivative of negative sine is negative cosine. So the third derivative of f at 0 will be negative cosine of 0, which is negative 1. Fourth derivative. The derivative of negative cosine is positive sine. And the fourth derivative at 0 will still be 0. Sine of 0 is 0. And now we're going to start repeating. So tell me, what would the fifth derivative be at 0? The fifth derivative would be 1. The sixth derivative would be 0 again. The seventh derivative would be negative 1, and that would keep on repeating. So, let me come over here. Sine of x. The Taylor series for sine of x will be, we start with our constant term, 0, plus. Now we go to the derivatives. So 1 times x minus 0, I'm going to write x minus 0 to the first over 1 factorial, plus 0 times x minus 0 squared over 2 factorial, plus negative 1, x minus 0 cubed over 3 factorial, plus 0, x minus 0 to the 4th over 4 factorial plus 1 x minus 0 to the 5th over 5 factorial plus 0 x minus 0 to the 6th over 6 factorial plus negative 1 x minus 0 to the 7 over 7 factorial, and that would go on and on. So sine x is approximately equal to, I'm not going to write the 0, this is just x. I'm not going to write the x squared. This would be minus x cubed over 3 factorial. I'm not going to write the x to the 4th term because of the 0 here. This would be a positive x to the 5th over 5 factorial minus x to the 7 over 7 factorial, and this pattern would keep on going. The next term would be plus x to the 9 over 9 factorial minus x to the 11 over 11 factorial plus dot dot dot. Keeps on going. I also need you to remember this one. That is the series that we played with in the introduction to Taylor series yesterday, or whenever I saw you last. Okay, next up, find a Maclaurin approximation for cosine x. So since it says Maclaurin, I know that we're centered at 0. Anytime it says Maclaurin, we're centered at 0. Going to go through the same process. F of x is cosine x. So f at 0 is cosine of 0, which is 1. F prime of 0. I'm sorry, f prime of x. The derivative of cosine is negative sine. So f prime at 0, the center, will be negative sine of 0, which is 0. F double prime of x, the derivative of negative sine is negative cosine. And the second derivative at 0 then will be a negative cosine of 0, negative 1. And at this point, we kind of know what's going to happen, I think, hopefully. The next derivative would be sine of x. At 0, that's back to 0. The fourth derivative would be cosine of x, and we've already done this. The derivative of cosine, or the fourth derivative of f at 0 will be cosine of 0, which is 1, and this will repeat itself. So cosine of x starts with 1 plus 0 times x minus 1 to the 1st divided x minus 0 to the 1st divided by 1 factorial plus negative 1 times x minus 0 squared over 2 factorial plus 0 x minus 0 cubed over 3 factorial plus 1 x minus 0 to the 4th over 4 factorial plus, and it keeps on going. So let's simplify that, clean that up. We start with 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. What would the next one be? It would be minus, because we're clearly alternating in sign. X to the 6th over 6 factorial plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial, and that would go on and on. And this is the last one that I need you to memorize. The last Maclaurin series I need you to memorize. Okay, here's how I remember these. I remember that cosine is an even function. Cosine is an even function. Back when we did even and odd functions in pre-cal, and probably in Algebra 2 as well, cosine has symmetry with respect to the y-axis. It's even. And look at all the even powers, even factorials. Also, cosine does alternate in sign, right? It goes positive to negative to positive to negative to positive to negative, and just like the series, it also alternates in sign. So I remember that cosine is even. So even, even, even. You can even think of 1 as even, because 1 is x to the 0 over 0 factorial. So you could even extend it to that if you want. I don't really do that. I just remember that cosine starts with 1. But you could totally do that. Sine is an odd function because it has symmetry with respect to the origin. So sine is odd. And we have all the odd powers. You could even think of that as x to the first over 1 factorial if you wanted to. So it has all the odd powers and odd factorials, and sine, like cosine, alternates in sign, so we are going to alternate in sign there. E to the x, I think of e to the x, it just has everything. It has all the evens, it has all the odds. And it is always positive, just like e to the x. E to the x is always positive. So it totally makes sense to me that this should be always positive. So always positive, and both even and odd. Powers and factorials. And that's how I remember it. So this is the process that you're going to go through for any function that you're trying to write a Taylor series or Maclaurin series for.